So, good afternoon, everyone, and welcome to a new session of our webinar series, DaSSWeb, Data Science and Statistics webinar. And today we have the great pleasure of welcoming Donato Malerba, who I think I can say it's a leading figure in machine learning and perhaps does not need an introduction. Donato has been a full professor of computer science at the Department of Computer Science of the University of Bari, Aldo Moro, since already 2006, where he has been before associate professor and researcher. He held the position of head of Department of Computer Science, served as director of the CINE National Lab on Big Data, and also acted as coordinator of the PhD program in computer science at some point. Professor Donato Malerba has been a member of the board of directors of the Big Data Value Association from 15 to 16, and a member of the steering board of the European Union Public-Private Partnership, Big Data. His research interests focus on data science, with machine learning, data mining, big data analytics, with applications in many different fields. He has coordinated local units of several European and national projects in the field, and currently he serves as scientific lead for a project Symbiotic AI, a national project FAIR, Future Artificial Intelligence Research. Donato Malerba has over 340 articles published in prestigious journals, conference proceedings, and also serves often as PC chair or co-chair or general chair at several international conferences, and has been involved in editorial boards of prominent journals in machine learning. Donato, thank you very much for having accepted our invitation. I should say that Donato has been a friend for a long, long time, and it's really a big pleasure for me personally to have Donato at DaSSWeb today. The floor is yours.
Okay, good afternoon, everyone. And first of all, a big thank to Paola and Maria Eduarda for their kind invitation and for hosting this wonderful webinar series. I'm really happy to be part of DaSSWeb, and I'm especially excited to share some thoughts today on data-centric AI, a paradigm shift that is reshaping how we think about AI development. Paola has already introduced me, so I would skip most of the words that I was saying about me, except for one thing, that I coordinate this Spoke 6 of the FAIR project, Future Artificial Intelligence Research. This is a national strategic project on AI, funded with 114 million euros. And I'm leading one of the 10 spokes of the project, the spoke on symbiotic AI. And I'm also leading the Interspoke project on data-centric AI and infrastructures. And that explains why I've focused this presentation on data-centric AI, because we are working on that currently in the FAIR project. Here is a glimpse of what I'll cover in this presentation. First, I'll trace the shift of paradigm from model-centric to data-centric. Then I'll delve into data-centric AI paradigm and its main research issues. Then I'll show some application domains evolving towards data-centric AI approach. I'll say just a few words on that. I'll revisit the CRISP-DM industrial methodology, having in mind this new approach. And finally, I'll draw some conclusions and I'll provide future perspectives in this field. Okay, let's start. And we start with a consideration that we are all in the data game. The vast amount of data being generated nowadays has fueled the rise of AI techniques across different areas, such as remote sensing, healthcare, and industry, just to mention some. And this surge is driven by the need to process and analyze large datasets to derive a meaningful insight and make informed decisions. Despite the close relationship between AI and big data, traditional AI methods have primarily operated within the traditional model-centric paradigm. This means that these methods have prioritized algorithm design and hyperparameter optimization, handling data as static entities, and overlooking issues related to data quality. For instance, in traditional AI workflows, a team working on classifying images, for instance, cats versus dogs, might proceed as follows. They use a fixed data set, like a subset of ImageNet, assuming it is clean and representative, spend weeks or months, maybe, tuning the model, experimenting with different CNN architectures, different hyperparameters, different optimizers, and then they evaluate performance with accuracy or F1 score and try to squeeze out small improvements via further tweaks. So we have a cycle here, basically on the model, and data is static. So what's overlooked? That the data set might contain labeling errors, duplicate images, or biases. For instance, it may happen that all dogs are in bright outdoor settings and cats are indoors, so we can conclude that dogs are in a specific environment and cats are in a different environment, and we can recognize and we can discriminate the dog from the cat according to the environment, which is not exactly what we expect. These data issues could mislead the model or limit its generalization, but are rarely inspected. Even after multiple iterations, performance plateaus, not due to the model, but because of the flawed data. The main advantage of this model-centric AI, of course, is that it has been instrumental in driving fundamental research, such as developing powerful algorithms that can generalize across many domains, from computer vision to natural language processing. This approach also gives us reusable models that serve as the backbone for instance, transfer learning and fine-tuning. However, there are some important downsides. First, replicating results can be a real challenge. Many models are complex, involve a large number of hyperparameters, and are often poorly documented. And this makes their reproduction difficult. This makes their reproduction. Models developed under the model-centric AI paradigm are typically tailored to specific data sets, making it challenging to transfer them across data sets also within the same problem domain. And second, and perhaps the more critical issue, this approach tends to treat data as a static asset. Issues like label noise, missing values, class imbalance are often neglected, and that can severely affect performance, no matter how sophisticated the model is. The question is this correct? The burden of dealing with data issues, for example, data noise, mostly rests with the models. So we solve them by considering more sophisticated models, but overlooking issues related to data quality, for instance, missing values, incorrect labels, outliers, may fail to produce desired results, despite significant investment of time and effort. And even the most sophisticated algorithms can't compensate for poor quality data. Focusing solely on algorithm design may overlook the critical importance of data quality and cleanness in AI projects. Without high-quality data, algorithms may produce unreliable or biased results, undermining their effectiveness and trustworthiness, just to use a term frequently occurring in AI literature. In many AI projects, data is treated simply as raw input, just fuel for training the model, rather than as a valuable asset that needs to be curated, maintained, and understood. And this mindset often leads to overlooking data quality entirely. But this indifference, we talk about data indifference, is not harmless. In fact, it can set off a chain reaction of problems known as data cascades. These are situations where small issues in the data, like labeling errors, missing context, biased samples, are ignored early on and then amplified at each stage of the development pipeline. The results, well, models that perform well in controlled settings fail when deployed in the real world. So, recognizing and addressing this data indifference is one of the first steps toward building more robust and trustworthy AI systems. In recent years, the AI community has increasingly recognized the importance of improving data quality and its direct impact on model performance. The key shift here is realizing that while models tend to be static, once trained, they don't change unless we intervene, data is inherently dynamic. It evolves over time. New sources, we have new formats, and data even changes in user behavior or range. And that's why the focus in moving towards data preparation as a core step is a core step in the development process. The goal is to build robust models that are less sensitive to small data variations, that can adapt to different scenarios with minimal retraining or adjustments. In other words, instead of constantly redesigning the model, we invest in making the data more representative, consistent, and meaningful. This is the data-centric AI paradigm, and as you can see now, the cycle goes back from the user to the data, and from data to model, and from model to the user. So we have included the data in the cycle. Some of the most high-profile machine learning projects in recent years have made one thing very clear. The real-world reliability of machine learning models depends much more on the quality of the training data than we might have previously thought. Even OpenAI, while training models like GPT-3 and Lee, has acknowledged that one of the major bottlenecks wasn't the model architecture or computing power, but rather errors and inconsistencies in the data itself. A similar story comes from Tesla. Instead of focusing solely on model innovation, they invested heavily in what they call a data engine, a system for continuously collecting, annotating, filtering, and improving data, assisted by their own models. And this strategy, as highlighted by Andrej Karpathy when he was director of AI at Tesla in 2021, enabled them to build more advanced autonomous driving systems than many competitors. Not necessarily because of better algorithms, but thanks to relentless model-assisted data refinement. In this slide, we take a closer look at how this data engine works. We have a data collection. Tesla collects a vast amount of data from its fleet of vehicles, including images and sensor data from various driving environments. We have a problem identification. The system identifies problems or edge cases where the AI model underperforms. We have data boosting. These identified problems are used to enhance the dataset, focusing on rare or challenging scenarios. We have then data labeling. Accurate labeling of data ensures that the models learn from high-quality, relevant examples. Then we train, or what better, we refine the model. The improved data set is used to refine or retrain the AI models, making them more robust and accurate. And finally, the new model is deployed into Tesla systems to identify real-world driving scenarios. And this iterative process continuously refines the AI models by focusing on data quality and relevance. This approach aligns with the principles of data-centric AI, since it emphasizes the importance of data over merely tweaking models. These examples show a clear shift in the industry, with many emerging data science and AI enterprises making data and not the models the centerpiece of their strategy. This shift is driving real benefits because we have a higher precision in predictions and recommendations. We have a faster deployment cycles since better data reduces debugging and model tuning. And we have a more standardized workflow making the data science pipeline more reproducible and scalable. Many of these enterprises are using a uniform model architecture across multiple applications. What varies is the data quality and domain-specific inputs. In particular, the focus is now on acquiring high-quality data and meaningful user feedback, which are essential for applying reinforcement learning techniques and delivering more human-centric and context-aware responses. This is exactly what's happening now when we use, for instance, large language models, and we try to apply to different domains. In short, the competitive edge is shifting now, not just to who has the best model, but to who has the best data and the smartest way to use it. So why do we need data-centric AI? Simply put, because better data is incredibly expensive, not just in terms of model accuracy, but in very real economic terms. According to a Harvard Business Review article of 9 years ago, but the research is still valid, poor data quality costs the US economy around $3 million every year. That's not just a technical problem, so it's a systemic one. These data issues affect almost every sector: healthcare, finance, transportation, public administration. And as data keeps growing in size, complexity, and sources, trying to fix it manually is no longer scalable. And as Andrew Ng puts it, the future lies in unbeginning AI, shifting focus from training even larger models to improving the data we already have, using the algorithms to detect, clean, and curate data more efficiently. That's exactly the core idea behind data-centric AI. Investing in data quality as a first-class citizen of the AI pipeline that we have seen. Even the most powerful AI system today, like ChatGPT, for instance, revealed the limits of relying on massive datasets and brute force learning. These models are like, just to use a sentence, a blurry JPEG of the web. They are trained on enormous volumes of data, much of it low quality or inconsistent, and then refined using huge amounts of human feedback to try and patch flaws. But here's the issue. Even with all that effort, the underlying data problems haven't been fully resolved. This approach simply doesn't scale, neither in cost nor in quality. As machine learning becomes deeply embedded in critical domains like healthcare, finance, transportation, and so on, we can no longer afford to treat data quality as an afterthought. Another reason why data-centric AI is gaining traction is the growing body of research evidence supporting its effectiveness. A great example comes from a study on image classification with noisy labels using the well-known CIFAR-10 dataset. Some researchers explored, and you see the reference here, explored what happens when models are trained with labeling errors. Their key finding: simple data-centric methods like adaptively identifying and cleaning mislabeled examples, actually led to more accurate models than complex, noise-tolerant model architectures. And this was shown in the work on confident learning by Northcutt and colleagues, where they demonstrated that improving the dataset itself can outperform trying to make the model smart enough to ignore the noise. It's a powerful message. Sometimes the best way to improve a model performance isn't to make the model more sophisticated, but to make data cleaner. The adoption of the DCAI or data-centric AI paradigm is mandatory for the success of the next generation of machine learning and deep learning tools. And we can identify three main interconnected steps in data-centric AI: training data development, inference data development, and data maintenance. Let's focus on training data development. The ultimate goal of a data-centric AI approach is to collect and produce rich, high-quality training data that can effectively support the training of decision models. This is achieved through two key processes. First, data creation, which involves intentionally designing and curating data sets that reflect the human intentions, human values, human priorities. This isn't just collecting data. It's about ensuring that the data aligns with what we want the model to learn. And second, data processing, which prepares the raw data for the learning stage. This includes steps like cleaning, formatting, balancing, validating, to ensure the dataset with both usable and to ensure that the dataset is both usable and meaningful. A data-centric approach involves a comprehensive data pipeline where each step is essential to building reliable, high-performing models. We start with data collection, which focuses on identifying the most relevant and useful data sets from sources like data lakes and data marketplaces. Next comes data labeling, which is time and resource intensive. So we increasingly rely on efficient techniques like crowdsources, consensus learning, semi-supervised, inductive learning to reduce costs and speed up the process of data labeling. And once labeled, data preparation ensures quality by handling noise, inconsistencies, and irrelevant features that can introduce bias or reduce accuracy. And then we apply data reduction to simplify the dataset without losing its essential information. And finally, we augment data to increase the size and the diversity of the dataset. Together, these steps ensure that the models are trained not just on more data, but on better, smarter data. Let's see now the inference data development. In a traditional model-centric AI approach, evaluation typically revolves around quantitative performance metrics like accuracy, computation time, memory usage. While these are important, they paint only part of the picture. What's often neglected are other critical dimensions of a decision model, such as its resilience to adversarial or unexpected inputs, its adaptability to changing data or environments, and its capacity to provide a reasoning or justifications behind its decision. That's why, in a data-centric perspective, we emphasize the inference data development step. The goal here is to generate new evaluation datasets that go beyond the surface level performance, and these datasets are carefully engineered to probe specific capabilities of the model or to provide richer insights into how the model behaves in different scenarios. Within the inference data development phase, there are a couple of key sub-goals designed to strengthen the evaluation of decision models. First, we have in-distribution evaluation. This involves generating samples that are aligned with the training data distribution. Why is this important? Because it helps us identify underrepresented groups, calibrate model predictions, and scrutinize decision boundaries. On the flip side, there's out-of-distribution evaluation. Here, the idea is to generate samples that are significantly different from what the model has seen during training. This includes techniques like adversarial example generation, which are useful to assess the model's robustness and generalization ability. In real-world scenarios, data isn't static. So it's continuously evolving, which means that keeping our models reliable requires ongoing data maintenance. And this step ensures that data stays high quality and relevant over time. And it includes three key sub-goals. First, data understanding focuses on making sense of a complex data sets. Second, the data quality assurance is crucial in dynamic environments. It involves continuous monitoring and quality checks using both objective metrics like accuracy and subjective assessments based on user expectations or domain knowledge. And third, we have a data storage and retrieval, which becomes increasingly challenging as data volumes grow exponentially. Underpinning all of this is the emerging field of MLOps, or machine learning operationalization management, which applies DevOps-like practices known in software engineering to machine learning workflows. It emphasizes the continuous monitoring of deployed models, especially to detect and manage concept drift, changes in the relationship between inputs and outputs, and data drift, changes in the input data distribution itself. We have identified three main challenges, three main research issues in DKI. First of all, how to collect, select, and valorize the data for an AI research project. In traditional model-centric AI, we often assume a perfect world. Data sets are clean, complete, and representative of a real-world distribution, but this assumption doesn't hold in practice. In real AI projects, data are rarely perfect. It may contain label noise, missing values, biases, distributional mismatches, and actually many popular data sets like ImageNet suffer from noisy labels. The figure that you see here shows examples of label errors in one ImageNet training set. These label errors have been discovered and are indicated in red. For instance, you cannot read maybe well here, but this this picture is labeled as an Atlantic outline, while it is a cargo ship. So this is just an example, but there are many others here. And this raises two central questions. How can we identify mislabeled or low quality data? One notable DKI technique is confident learning, which attempts to estimate the likelihood that the label is incorrect and systematically clean and refine training data sets. Another research issue concerns on how can data quality and consistency be ensured in AI research project. A foundational challenge in AI projects is that low quality data can silently propagate errors through the entire life cycle of a month, often resulting in technical debt and performance failures down the line. In a pivotal study by Google researchers, the concept of data cascades that I mentioned before was introduced to describe these negative downstream effects of poorer data quality. The study involved 53 AI practitioners across the USA, India, East and West Africa, covered high-risk sectors such as healthcare, agriculture, finance, public safety, and education. And what was found? That 92% of participants experienced at least one data cascade in their projects. These cascades emerged from issues such as incomplete or unrepresentative representative data, or misaligned assumptions between data creators and model developers, or lack of iteration between model results and data refinement. And to combat these issues, recent research on data-centric AI focused on systematically improving data quality throughout the AI pipeline, minimizing error propagation at each stage, from collection to model deployment, and on embedding validation and monitoring routines to track data drift, inconsistency, and quality degradation. Another research issue is related to how should we evaluate AI systems. The evaluation is a crucial phase before deploying any AI system in real-world scenarios. And traditionally, under the model-centric paradigm, evaluation primarily revolves around performance metrics such as accuracy, F-score, measured on fixed test datasets. Well, it's useful, but this narrow focus often overlooks key real-world factors. In contrast, in the data-centric AI approach broadens the scope of evaluation, reflecting the complexity and dynamic nature of real-world data. And instead of focusing solely on static accuracy, DKI encourages the evaluation of AI systems based on a more holistic set of criteria, such as data dynamics. How does the model perform as the data distribution evolves over time? Robustness to adversarial data, Can the model withstand adversarial or out-of-distribution inputs? Explainability. Can the model's decision be understood and justified, particularly in sensitive domains? Resilience. How well can the model maintain acceptable performance when exposed to noise or incomplete data? Reusability and adaptability. Is the model adaptable to new tasks or domains without requiring full training? And these aspects highlight the inadequacy of relying solely on test accuracy as an evaluation proxy. While manual exploratory data analysis remains essential, of course, data-centric AI offers a more systematic and automated approach to improving real-world datasets. It typically manifests in two forms: AI algorithms that interpret and organize data to enhance learning, such as curriculum learning proposed by Benjo, where models are trained progressively on easier data, and AI algorithms that modify data to improve model performance, like confident learning, proposed by Northcutt a few years ago, which filters mislabeled data to reduce noise. In both cases, these techniques rely on feedback from trained models to assess the data quality, marking a shift from model-centric to data-aware strategies that tightly couple dataset refinement with model development. Data-centric AI research encompasses a range of techniques aimed at improving the quality of data. And among these techniques, outlier detection and removal helps eliminate abnormal or irrelevant examples, while error detection and correction addresses mislabeled or inconsistent entries. In settings with crowdsourced labels, consensus methods play a crucial role also in inferring reliable ground truths from diverse annotations. Data augmentation expands datasets by introducing variations that reflect domain knowledge, and the feature engineering and selection refine how information is represented, improving model interpretability and performance. Furthermore, active learning strategically identifies the most informative data points to be labeled next, reducing annotation cost. And finally, curriculum learning structures the learning process by presenting training examples in an order that moves from simpler to complex, facilitating smoother and more robust model convergence. DeepAI promises to transform many industrial and data science domain applications by gaining decision-making efficiency and effectiveness through insights derived from data. At present, the use of a DeepAI paradigm has emerged as a new trend in at least 3 data domain applications. These studies that you see listed here in the realm of spatial data analysis underscore how DeepAI strategies, including contrastive learning and domain adaptive feature design, are redefining how spatial data is processed, enabling more resilient and efficient AI systems, for instance, in Earth observation. And we do have a European project on that, and we are actually working on a data-centric pipeline. Data-centric AI is also playing a pivotal role in transforming traditional healthcare. These contributions reported here, mentioned here, reported importance of DKI in reshaping traditional healthcare into digitized patient-centered healthcare and in data-centric healthcare for sustainable healthcare. And in this also in this work here by Luli, we see the model-centric approach, how we overcome the problem of the model-centric approach that traditionally prioritized the aggregation of larger-scale data sets to train increasingly complex models, often placing the burden of data curation and understanding on data scientists. However, this assumption does not hold in many real-world scenarios, especially for small and medium-sized enterprises, which frequently face critical barriers, such as limited data sets, sparse and noisy labels, data drift, and a general lack of in-house expertise in machine learning and deep learning. And in this context, the model-centric view often proves impractical and unsustainable. And in contrast, the data-centric paradigm offers a more flexible and accessible framework. As described in the paper by Luli and company, this shift is particularly impactful in industrial sectors, where a tangible, adaptable DKI development process can be deployed despite limited resources. And now let's move to the methodological aspect. We all know that we all know about CRISP-DM, cross-industry standard process for data mining. It's the methodology developed 25 years ago to support, let's say, KDD processes. And actually, CRISP-DM, if we have a look at this methodology, we can say that it supports a data-centric AI approach, although it can accommodate model-centric perspectives as well. Why CRISP-DM is more aligned with data-centric AI? Because it puts emphasis on data understanding and preparation. So we have two phases of the process, CRISP-DM methodology, that are focused on the data. And the methodology encourages iteration, not only on the model, but also on the data preparation phase. Modeling is only one part, and also the evaluation is holistic. It's not based only on the results of the precision metrics used typically to evaluate the models produced by the modeling phase, but the evaluation phase supports the data-centric philosophy where understanding and improving the data pipeline is crucial. But the rise of data-centric AI calls also for a rethinking of this methodology to better align with the realities of today's data challenges. And in this revised approach, the first phase becomes even more crucial. We call it this first phase understanding and definition. Here we begin by defining the business objectives, of course, and the stakeholders' requirements, just like in CRISP-DM. And a key annotation, however, in the data-centric mindset is the early identification of the types of data we will need: text, images, video, and structured data. This is where we shift the focus from what models we run, to what data do we have or need, and is it good enough? This leads up to a preliminary assessment, not of algorithms, but of data availability and quality. Are there missing values? Is the data biased? Do we have enough samples from critical subgroups? These are the kinds of questions that need to be asked at the outset and not after the model development. As we dive deeper into the data-centric AI approach, one of the most pivotal phases we encounter is data collection labeling. And this phase is crucial because, as we know, the quality of the data we use often defines the quality of the performance we produce. First, the data collection itself is no longer just about pulling from a single source. Data now comes from a diverse array of sources, from the web, sensors, and databases. And we need to understand where our data is coming from and ensure that it's representative of the problems we're trying to solve. And once we have gathered all this data, we face the challenge of data labeling. Labeling is the backbone of supervised learning, and ensuring that the data point is correctly annotated is a critical task. And manual annotation has been a traditional approach, but it's labor intensive and error prone, and automated annotation can help, but only when combined with careful validation. And the key here is ensuring quality and consistency across annotation. And to boost this accuracy, we often turn to expert annotators, but we should also consider active learning to process. This helps to reduce costs, and it allows the model to guide the labeling process, focusing human effort where it's needed. In another revision, still revising CRISP-DM, we have another crucial phase that we call data cleaning and augmentation. And in this case, what is relevant how we remove noisy, duplicate, and inconsistent data, and how we treat automatically missing values and we correct labeling errors, how we use outlier detection techniques to remove abnormal examples, how we perform a data augmentation. That is, we generate synthetic examples from minority classes to increase the diversity and robustness of the dataset. And here, it's also important how we perform data enrichment, how we incorporate external knowledge or domain-specific information to enrich the dataset. Another important phase is data selection, prioritization, transformation, and feature engineering. And I'll focus here just on the selection of most representative instances to avoid redundancy, and the ordering of training examples, what we have called the curriculum learning. And finally, the evaluation and validation is one of another important stage of our data-centric approach to AI. We not only work on usual metrics, but we define data quality metrics, and we work we consider also this inter-annotator agreement, class imbalance, representativeness of application domains as metrics to improve continuously the quality of the data that we have um, uh, collected. And we evaluate the KDD process on the base of this data quality metrics as well. And it's important here also to use explainability techniques to verify whether model decisions align with data corrections and domain knowledge, or to identify potential biases or inconsistencies. In this phase, we also consider the generation of new evaluation sets that offer more detailed insights into the model. And finally, revisiting CRISP-DM, we think that we have to work also on the automated data quality monitoring. We need to implement continuous monitoring tools to detect data drifts and quality degradation during model deployment. So if we compare CRISP-DM with the different phases of CRISP-DM with the phases that I mentioned before, we see some main differences, and that explain the need of more focused methodologies for supporting data-centric AI. Well, to conclude, the data-centric AI paradigm signifies a fundamental shift in AI design, system design, with data science applications, and prioritizing a data-centric approach over a model-centric one. And the future research in data-centric AI is expected to focus on the following challenges. First challenge, how to inference data holds the same weight as training data. The fact is that the same level of rigor and attention that we apply to curating training data should also be applied to the data the model will encounter in the deployment, that is in the inference time data. And in DKI, inference data is not passive. So we do expect data that will come and we test the model on this data. Inference data is used to continuously update or audit the training set. So if we have a misclassifications at inference, we use those to enrich the training data set. And if we have a domain shifts in incoming data, we trigger rebalancing or augmentation strategies. And also, another challenge is transforming raw data into smart data. According to Garcia, Gil, and Etali, smart data is the challenge of acquiring knowledge from raw big data. And the goal is to separate the raw from the intelligence, where raw is intended as volume velocity that characterize big data, while intelligent is related to the veracity and the value of the big data. And the key idea is that not all big data is valuable. Only high quality subsets lead to meaningful knowledge. And the implication for DKI is that we have to focus on curating high quality data subsets, not just collecting more data. Another challenge in DKI is the explainability as an enabler of data model co-design. Co-designing inputs and models means that we jointly design data representation and model structures involving domain experts, data scientists, AI engineers. And why it is important? Because it boosts adaptability and transferability of models. And in this co-design, explainable AI is crucial because it can contribute to building high-quality AI systems in collaboration with domain experts. And another challenge is related to data bias and fairness. Data bias exists across all applications, but the level of impact varies. We can have low-risk applications and high-risk applications. And for the latter, for high-risk applications, it's important to mitigate and control data bias. And so all the techniques for bias detection, for inclusive data collection strategies, for inclusive data collection, for fairness-aware learning and sensitivity analysis are useful in this to support, to provide answers to this challenge that we have to face in a data-centric AI perspective. And finally, the high quality. As I said, accuracy, precision, recall are metrics used in a traditional focus. Modern need are fairness, bias mitigation, model robustness. And there are recent works that show that it is possible to classify bias mitigation techniques across three stages: pre-processing, data editing, sampling, in-processing, fair loss functions, constraints, and post-processing, adjusting model outputs. And the key shift here is from model-centric performance to controlled data management. So this gives a perspective on what are the research challenges that we have in data-centric AI. If you are interested, we have, together with Vincenzo Pasqua di Bisceglie, we have worked on data-centric AI, on a special issue on data-centric AI, and we have summarized some of these ideas in the editorial of this special issue. In the data-centric, the title of the paper is Data-Centric AI, and you can find more details on also examples of research data-centric AI in that special issue. Okay, thank you very much. You can, and finally, if you are interested in this topic, you can attend, or you can even submit your papers to the workshop on the second international workshop on data-centric artificial intelligence that we are organizing together with Vincenzo for the European Conference on Machine Learning and Principles and Practice of Knowledge Discovery in Databases. And the workshop will be held in Porto next September. Thank you again.